Before you start using SQL queries, you should know how governor limits and indexes work in Salesforce. Otherwise, there is no point in even trying, because it will surely be a bad SQL query. Basically, you don't need to understand what an index is under the hood. It's enough to know which standard fields are indexed by default, and if you want to add index to the custom field, you can mark it as external ID or unique. The external ID field may be used to reference the ID from another external system. You can create external ID under the following fields. The unique ID field is a setting which prevents the same value from being used in multiple records for any specific field. External IDs are often created with the unique ID setting, so that the external ID will be unique to each record. A custom index can't be created on these types of fields. It is possible for Salesforce customers to request a custom index from Salesforce support by creating a support case and including a SQL query with the indexed field. The easiest way to see which fields on a given object are indexed is to check for a check in the index column in the list of the object fields in setup. The platform maintains indexes on the following fields for most objects. Again, the following fields are indexed by default. Index selectivity exceptions. When building your queries, always strive to avoid these things. Fields not indexed by default are automatically indexed when the Salesforce optimizer recognizes that the index can improve performance of frequently run queries. So you should know what an optimizer is, and it's important. Salesforce backend database uses Oracle, but Force.com uses its own version of a query optimizer to evaluate cost-based queries. It means for even the simplest queries, there are usually several possible ways to get the job done. The database server has to figure out which way is going to be the fastest. Server builds an execution plans and assign a cost in numerical form to each operation inside the execution plan. It then uses the cost to determine which execution plan to use. Like most cost-based query optimizers, the one that Salesforce uses relies on statistics gathered about the data. Most statistics are gathered weekly, but the system also generates pre-queries that are cached every hour. The query optimizer evaluates SQL queries and social searches. It acts as a sort of a traffic cop by routing queries to the appropriate indexes. Platform creates an index table that contains a copy of the data along with information about the data. The platform builds a standard database index on this index table. The index table places upper limits on the number of records that an index search can effectively return. By default, the index tables don't include records that are null. When the optimizer determines that the given filter condition exceeds the corresponding selectivity threshold for an index, the optimizer does not use the index because the overhead of using the index is not optimal. For thresholds, see Salesforce Query Search Optimization Developer Cheat Sheet. You can stop here, but if you want to dive a little deeper, let's continue. Salesforce does not tell us much about its database. We know it uses Oracle and that's it. The Btree index is the default index type in Oracle, so we assume that Salesforce uses Btree indexes. Maybe in some parts it uses bitmap indexes or hash indexes, but I didn't find any docs on this subject. Let's start from the beginning. Logarithmic runtime widely used in databases, O of log n, in big O notation. Big O notation helps us to estimate the efficiency of given algorithm. It means how slow algorithm run if input size grows. Logarithmic algorithm binary search is the most effective. Logarithmic means with every operation we cut input in half. Binary search tree is the predecessor of B-trees, and each root node has up to 2 child nodes. Each node in a tree is a subtree. It is also a root node, so each root node with 2 children or 1 child is a separated binary tree. Again, in binary trees, each node can have a maximum of 2 children. hence the name binary. To walk through the binary search tree, we have two methods. Depth first traversal. Start at the top and move all the way down of the tree. And breadth first traversal. Start on the top but move across each level before go down to the next level. For each node that we access, we perform some operations, because each node contains some data. Binary search uses recursion. Recursion is a process in which a function calls itself directly or indirectly. The most common example is Fibonacci sequence. Take a look. I will use JavaScript because it's the fastest way to create examples. Binary search tree is working well only if it's balanced. It means most nodes have left child and right child. Now we got closer to the B-trees. This is an example of B-tree of minimum order 5. There is a lot of info about B-tree, so you should research for yourself. Here are important rules for creating B-tree. All leaves will be created at the same level. Remember breadth first traversal method. B-tree is determined by a number of degree, which is also called order, specified by external actor, like a programmer, referred to as M onward. The value of M depends upon the block size of the disk on which data is primarily located. To understand the use of B-trees, we must think of the huge amount of data that cannot fit in the main memory. When the number of keys is high, the data is read from the disk in the form of blocks. Disk access time is very high compared to the main memory's access time. The main idea of using Btree is to reduce the number of disk accesses. The height of B-trees is kept low by putting the maximum possible keys in the B-tree node. Generally, the B-tree node size is kept equal to the disk block size. Since the height of the B-tree is low, so total disk access for most of the operation are reduced significantly compared to the balanced binary search trees. All leaves in B-tree are at the same level. The root may contain a minimum of one key. Number of children of a node is equal to number of keys in it plus 1. All keys of a node are sorted in increased order. B-tree grows and shrinks from the root, which is unlike binary search tree. Binary search trees grow downward and also shrinks from downward. Like other balanced binary search trees, the time complexity to search, insert or delete is O of log n, which is again a logarithmic runtime. Insertion of node in B-tree happens only at leaf node. And little bit about social at the end. Salesforce uses the open source search and indexing engine Lucene to power Social. Social also has indexes, but you don't have much control over how search indexes are used, which is a good news, because it means that writing social queries is easy. You won't be using social much or at all, so there is no point to explaining it here. The only thing I want to mention is that the nickname search applies only to account, contact, lead, and user objects. It's an interesting option, but my guess is it is for Experience Cloud. That's it.